When paralleling wires, it's essential to accurately calculate the current carrying capacity and provide appropriate overcurrent protection. Addressing the question of whether two sets of paralleled wires are considered as four current carrying conductors, the answer is yes. Consequently, the percentage adjustment specified in Table 310.16 of the National Electrical Code, or NEC, must be applied based on the total number of current carrying conductors. In the scenario of four current carrying conductors arising from two sets of paralleled wires, an adjustment factor of 80% is required. This adjustment accounts for the reduced heat dissipation capability when multiple conductors are bundled together. Let's review the calculations provided and make necessary adjustments. Firstly, the largest motor's contribution is 125% of its full load current, or flow, which is 120 amps multiplied by 1.25, resulting in 150 amps. Secondly and thirdly, the other two motors each contribute 93.1 amps at 125%, resulting in 93.1 amps multiplied by 1.25, or 116.375 amps each. It appears there was a miscalculation that did not take the 125% into account. The total motor load is calculated as 150 amps plus 116.375 amps plus 116.375 amps, which equals 382.75 amps. Now let's address the heater load. The total heater wattage is 17,500 watts plus 21,600 watts plus 22,100 watts plus 1,200 watts, totaling 62,400 watts. Given a 480-volt three-phase system, the heater current is calculated by dividing the total wattage by the product of the voltage and the square root of 3. That is 62,400 watts divided by 480 volts multiplied by the square root of 3, which is approximately 75 amps. Applying the 125% factor to the heater load yields 75 amps multiplied by 1.25, equaling 93.75 amps. The total load is then the sum of the adjusted motor load and the adjusted heater load, which is 382.75 amps plus 93.75 amps, resulting in 476.5 amps. Based on these calculations, the initial assessment that the nameplate full load amps, or flow, of 442 amps was acceptable may be incorrect, as 476.5 amps are calculated. To determine the appropriate wire size for parallel conductors, consider the ampacity of 4/0 THHN wire, which is 260 amps. When paralleled, two sets of 4/0 THHN wires provide a combined ampacity of 520 amps before adjustment. However, with four current carrying conductors, the adjustment factor of 80% must be applied. This yields an adjusted ampacity of 520 amps multiplied by 0.80, which equals 416 amps. This adjusted ampacity of 416 amps is less than the calculated total load of 476.5 amps, indicating that a larger wire size is required. Moving on to the matter of overcurrent protection for parallel wires, it's crucial to understand the applicable exceptions in Section 310.4 of the NEC. Exception number 2 of Section 310.4 does not apply in this scenario because the conductors are not supplying control power and are not rated for the full load current shared by the parallel conductors. Therefore, each individual wire must be provided with overcurrent protection rated for the full load current it carries. Given that each 4/0 THHN wire has an ampacity of 260 amps, the overcurrent protection should be rated accordingly. In summary, the calculations indicate that the original wire size may be insufficient based on NEC guidelines due to the ampacity adjustments for current carrying conductors. Parallel conductors are subject to adjustments based on the number of current carrying conductors in a raceway or cable. You must size the conductors such that the ampacity of the parallel conductors after adjustment is equal to or greater than the calculated load. If the adjusted ampacity is less than the load, a larger conductor size will be necessary. If 4/0 THHN isn't sufficient, a larger size, like 250 kcmil, may be considered, or even running 3 sets of conductors to meet ampacity requirements. Next is the overcurrent protection of parallel conductors. Each parallel conductor must be protected at its ampacity. This means that each 4/0 THHN conductor with an ampacity of 260 amps would need to be protected by a 260 amp overcurrent protective device. If the conductors are connected to a single overcurrent protective device, the conductors must be sized such that the overcurrent protective device protects the conductors, and the conductors can carry the load. It is worth noting that simply increasing the size of the overcurrent protective device is not permitted, as it would not provide proper protection to the conductors. Let's break this down into a more detailed explanation of each key area. Firstly, conductor ampacity and adjustment factors. The ampacity of a conductor is its current carrying capacity in amps. This value is typically found in NEC tables, such as Table 310.16 for conductors rated 0 through 2000 volts. The table ampacity is based on specific conditions, including a certain ambient temperature and a limited number of conductors in a raceway or cable. When these conditions are not met, adjustment factors must be applied. Adjustment factors for ambient temperature are found in the NEC and are used when the ambient temperature around the conductor is higher than the temperature listed in the ampacity table. The adjustment factors for the number of current carrying conductors are also found in the NEC and are used when more than 3 current carrying conductors are in a raceway or cable. These adjustment factors reduce the conductor ampacity to account for the increased heat generated by multiple conductors in close proximity. Secondly, calculating the load current. The total load current is the sum of all the individual loads in the circuit. This includes motor loads, heater loads, and any other electrical equipment connected to the circuit. For motor loads, the NEC typically requires sizing conductors and overcurrent protection based on 125% of the motor's full load current, or FLA, as indicated on the motor nameplate. This accounts for the motor's ability to draw more current during startup and under load. For continuous loads, which are loads expected to operate for 3 hours or more at a time, the NEC requires sizing conductors and overcurrent protection to 125% of the continuous load current. This ensures that the conductors and overcurrent protection are not overloaded during extended operation. Thirdly, parallel conductors. The NEC permits conductors to be connected in parallel under certain conditions. This is typically done to increase the ampacity of a circuit beyond what a single conductor can handle. When conductors are connected in parallel, they must meet specific requirements outlined in the NEC, including being the same material, same size, same insulation type, and same length. In addition, all parallel conductors must be terminated in the same manner. Fourthly, overcurrent protection. Overcurrent protection is designed to protect conductors and equipment from overloads and short circuits. The overcurrent protective device, such as a circuit breaker or fuse, must be sized to protect the smallest conductor in the circuit. In the case of parallel conductors, each conductor must be protected at its ampacity. This can be achieved by using individual overcurrent protective devices for each conductor, or by using a single overcurrent protective device sized to protect the smallest conductor. Fifthly, NEC references. Section 310.16 of the NEC contains ampacity tables for conductors. Section 310.15 addresses ampacity calculations and adjustments. Section 310.4 covers conductors in parallel. Article 670 pertains to industrial machinery, addressing the requirements for supply conductors and overcurrent protection. When applying these principles, always refer to the latest edition of the NEC and consult with a qualified electrical professional to ensure compliance with all applicable codes and standards. Also important is understanding the specific characteristics of the equipment being powered, including the motor's service factor, temperature rise, and any specific requirements outlined in the manufacturer's instructions. In addition, consider any future expansion or changes to the load requirements to ensure that the electrical system is adequately sized for anticipated needs. In summary, paralleling conductors requires careful consideration of ampacity, adjustment factors, overcurrent protection, and adherence to NEC guidelines to ensure a safe and reliable electrical installation. Always consult with qualified professionals to ensure compliance with all applicable codes and standards. The first step is to accurately determine the load requirements, including motor loads, heater loads, and any other equipment connected to the circuit. Obtain the full load current, or flow, from the motor nameplates and consider any continuous loads that may require additional ampacity. Secondly, calculate the total load current by summing up all the individual loads, applying the 125% factor to motor loads and continuous loads as required by the NEC. Thirdly, determine the appropriate conductor size based on the calculated load current and the ampacity of the conductors, considering the adjustment factors for ambient temperature and the number of current carrying conductors in a raceway or cable. Fourthly, if paralleling conductors, ensure that they meet the requirements outlined in the NEC, including being the same material, size, insulation type, and length. Fifthly, provide overcurrent protection for each conductor at its ampacity, using individual overcurrent protective devices or a single device size to protect the smallest conductor. Sixthly, verify that all calculations and installations comply with the latest edition of the NEC and any other applicable codes and standards. Finally, consult with a qualified electrical professional to review the design and installation to ensure safety and compliance. It is important to note that electrical codes and standards can vary depending on the location, so it is essential to consult with local authorities and qualified professionals to ensure compliance with all applicable regulations. In addition, consider any specific requirements or recommendations from equipment manufacturers to ensure proper installation and operation of electrical equipment. Remember that working with electricity can be dangerous, so always take precautions to protect yourself and others from electrical shock and other hazards. Turn off power to the circuit before working on any electrical components, use appropriate personal protective equipment, and follow safe work practices at all times. By following these steps and working with qualified professionals, you can ensure a safe and reliable electrical installation that meets all applicable codes and standards. This process ensures that the electrical system is designed and installed in a manner that protects people and property from electrical hazards such as overloads, short circuits, and electrical shock. Furthermore, regular maintenance and inspections of electrical systems are essential to identify and address any potential issues before they become a safety hazard. This includes checking conductors for damage or wear, testing overcurrent protective devices, and ensuring that all connections are tight and secure. It is also important to educate occupants and employees about electrical safety and how to respond in the event of an electrical emergency. This can include training on how to recognize and report electrical hazards, how to use electrical equipment safely, and how to evacuate a building in the event of a fire or other electrical emergency. By taking a proactive approach to electrical safety, you can minimize the risk of electrical accidents and ensure a safe environment for everyone. This includes staying up to date on the latest codes and standards, using qualified professionals for all electrical work, and conducting regular maintenance and inspections of electrical systems. In addition, it is important to promote a culture of safety in the workplace and at home, where everyone is aware of electrical hazards and takes steps to prevent accidents. In conclusion, ensuring electrical safety requires a comprehensive approach that includes proper design and installation, regular maintenance and inspections, education and training, and a commitment to following safe work practices. By working together and taking responsibility for electrical safety, we can create a safer environment for everyone. It's important to reiterate that working with electricity can be dangerous, and it is essential to prioritize safety at all times. If you are not comfortable working with electricity or are unsure about any aspect of the electrical system, it is best to consult with a qualified electrical professional. They have the knowledge and experience to safely and effectively address any electrical issues and ensure that the electrical system is in compliance with all applicable codes and standards. Remember that electrical safety is not just a matter of following codes and standards, it is a matter of protecting lives and property. By taking the time to understand electrical hazards and implement appropriate safety measures, you can help prevent electrical accidents and create a safer environment for everyone.